Okay, good morning, folks. I guess it's my task to wake you up this morning. The speakers in the afternoon had the task of sort of keeping you awake after a long day of activities, but hopefully you've had your coffee this morning. And I'd like to tell you a little bit about setting the scene for the search for life in the universe, and I'll be following up with another talk that's really getting into the details of how we do that. But just to sort of give us some context here, many of you have probably flown over Greenland. I grew up in the UK, but I now live out in California, and I love to take the window seat when I'm flying back from San Francisco to London to see views like this, really incredible views. And now we're sort of in amongst these amazing fjords, seeing the ice going past. But when you're looking down from a plane at scenes like this, it really looks pretty inhospitable. And I think some of the earlier explorers that came out here also saw this sort of forbidding environment. We've been pretty lucky here with the weather, in the middle of August, to see sunny days and to see, really Greenland at its best. But it's a pretty inhospitable place, I think, for a lot of the year. But there's wildlife here. How many of you have seen a muskox so far on this trip? Nobody? Well, then I think there must be no muskox in Greenland because we've never seen them, right? I mean, that's the sort of conclusion about life elsewhere in space that some people make. We haven't seen any evidence of it, so it must not exist. But this life is out there, even in these extreme environments. And in fact, there are environments even more extreme than this. A few years back, scientists discovered a bacterium which they named Chrysobacterium greenlandensis for where it was found. And it was found under the ice at high pressures, in extreme temperatures, and it had survived, they think, for 120,000 years in those conditions. So life really finds a way, even in extreme conditions here on Earth. And of course, human life finds a way here as well. In those views from the plane, you don't see the signs of habitation like we saw yesterday and like we'll see in the other villages that we're going to visit. But it's there. Life finds a way, and you just have to look in the right place with the right tools at the right time, and you have a chance of finding it. And life finds a way in extreme heat as well. So this is in the Marianas Trench. This is about 3 kilometers deep. The water that's coming out of these black smokers is at 300 or 400 degrees Celsius. And life is happy down here in its own little ecosystem, really kind of crazy, extreme environments compared to what we're used to. But you see these sort of shrimp-like creatures and crabs that are just, surviving down at really unimaginable depths and unimaginable pressures and unimaginable temperatures. And if you've ever been to Yellowstone and seen places like Grand Prismatic Spring, there are these extremophile bacteria that live in highly acidic environments that are very hot and give these sort of amazing colors here. And in fact, these are seen as models for the early Earth. And scientists that are studying these environments are also looking into the origins of life on Earth, where the conditions were more extreme even than they are now, and then using these as analogs for the search for life on other planets where conditions can be really pretty extreme compared to what we find here on Earth. And so I'm sort of leading up to this, when you look up at the night sky, we haven't seen the aurora yet on this trip. Hopefully the sky will clear and we'll get a chance to see the sort of cosmic light show. Maybe we can talk a little bit about that later in the trip if we get that opportunity. But looking beyond, as the ancient people settling these lands looked up at the night sky and saw these stars, people have really been wondering, I think, since the beginning of time, are we alone in the universe? Is the life out there elsewhere around these glowing orbs in the night sky? And so here's a quote from Lucretius in 60 BC, who asserted, "Nothing in the universe is unique and alone, and therefore in other regions there must be other Earths, inhabited by different tribes of men and breeds of beasts." So really, are we alone? It's one of the most profound human questions. 1,500 years later, Nicholas of Cusa said, "Life as it exists on Earth in the form of men, animals, and plants is to be found, let us suppose, in the solar and stellar regions. Rather than think that so many stars and parts of the heavens are uninhabited and that this Earth of ours alone is peopled, we will suppose that in every region there are inhabitants." And so you'll see both of these quotes sort of involved supposing that there's life out there. But how are we actually going to go and test that? I'm going to talk about that in the second talk, how we actually apply these tools and techniques of modern science to try and answer this question. But I want to take us back even further to give us a little bit of context. So 13.8 billion years ago, we now have observations that show the universe began in a hot Big Bang. And in about the first second protons formed, and then the universe was a big fusion reactor, basically turning hydrogen into helium for about the first 20 minutes. So about 20 minutes later, the universe had cooled to about 1 billion degrees, and that nuclear fusion stopped. And so most of the hydrogen that was made shortly after the Big Bang and most of the helium that was made, by that point, the helium nuclei and the hydrogen nuclei existed by about 20 minutes. And so at the end, there was about 3/4 hydrogen and 1/4 helium with trace amounts of heavier elements. By about 380,000 years later, the universe had cooled further to about 3,000 degrees, and those nuclei and electrons combined to form atoms. So the first atoms formed, and then they left this imprint. This is sort of the universe's baby picture, the cosmic microwave background. Everywhere you look, in all directions in the sky, you see this glow that's left over from the Big Bang. And the red and blue spots here are very tiny variations in color, about 1 part in 100,000. Variations in temperature of about 1 part in 100,000, and variations in density. So the universe was very smooth at this point, but these tiny little fluctuations went on to grow by just the force of gravity to form the stars and the galaxies and all of the structure that we see in the universe today. And so really, you're looking at sort of our ancient origins here, basically. And then hundreds of millions of years later, the first stars started to form. I actually saw from the plane on the way over here just before dawn. It was a really beautiful sight, Orion kind of lying on its side. And if you look closely at the sword in Orion, you'll see that the middle star is not actually a star. It's a nebula, the Orion Nebula. And you can see this pretty clearly with your naked eye. And we're going to go to a slightly better picture here from the Hubble Space Telescope. And so this is a stellar nursery. This is where stars are born. And as those stars are born, they're taking up the hydrogen and the helium that we talked about that was formed in the Big Bang. And there's these big fusion reactors in the centers of stars, which are generating heavier elements. And then massive stars evolve to become red supergiant stars like Betelgeuse. So you see this star, don't say that 3 times, by the way, but you see the red star in the top left is Betelgeuse. And stars like this fuse the lighter elements to form carbon, neon, oxygen, silicon, and eventually iron. And then Betelgeuse, oh dare I said it 3 times, is going to end its life as a supernova. And when it explodes, it will be really one of the brightest objects in the sky. And there are historical examples in the historical record here. The Hohokam people in Arizona, it's a little difficult to make out from this photograph, but they sketched on this rock something that looks like a scorpion and something that looks like a bright star. And so when astronomers, this was about 1,000 years ago, when astronomers went back 1,000 years later and looked in Scorpius, they found this shell of expanding gas, a supernova explosion, which we now trace to a supernova that exploded in 1006. And it was actually seen by the Chinese and noted in their records. It was seen by various other observers of the sky at that time. So when these massive stars explode as supernovae, like this one, supernova 1006, would have been 16 times as bright as Venus in the sky, so visible in the daytime. And they take these elements that have been fused together in the stars and cast them out into space. And then they get recycled in the next generation of stars in a nebula like this one. This is the Tarantula Nebula observed by the James Webb Space Telescope. And recycled into the next generation of stars and planets and raw materials that then can form materials like we see around us here. We heard yesterday about these 4 billion-year-old rocks. Those rocks were formed when the Earth formed, or shortly after the Earth formed in the original nebula that formed the solar system, and again, recycling the earlier generation of stars. And if you hold up your hand and you look at the constituents of our own body, Carl Sagan and Joni Mitchell made the point that we're made of stardust, right? And it's literally true. The stardust in your body, the hydrogen in the water that makes up 70% of our body was formed in the Big Bang, and the calcium in your bones and the iron in the hemoglobin in your blood was formed in a massive star like Betelgeuse and then seeded out into space in a supernova explosion and recycled about 4.5 billion years ago into the solar nebula. And again, all of the material that we see around us, the rocks, the water, all of this has cosmic origins. And I think this sort of big picture, seeing things in this context is really quite humbling, and also sort of, again, just makes us think about these questions of origins and life and how life gets started. And again, when you look up at the night sky, and you see billions of stars in our Milky Way galaxy, you have to ask yourself the question, did this happen anywhere else, right? The conditions for life, well, let's say the ingredients for life, we now know are everywhere. Are the conditions for life everywhere? That's what we're going to explore in this lecture and the following lecture. And if you put the conditions and the ingredients together, is life inevitable? Or is it just a rare chance, like here on Earth, do we find ourselves sort of in a lucky environment where life just happened to arise? So I want to take us a little bit further forward to the early 20th century. I don't know, probably some of you are better than your kids or grandkids at reading cursive, so maybe you'll be able to figure out what Nikola Tesla was writing about here in 1937. But he says, undoubtedly there are myriads of planets in the universe which are or will be abodes of life in its highest forms. The same formative principles must be operative in the building up of the bodies of the inhabitants, and their perceptions of the external world must be closely similar to ours. It is highly probable that many are as far or even more advanced than ourselves. Codes for communication and mutual understanding can be readily formulated on the bases of commonly perceived universal truths. By my inventions, it has become possible to transmit considerable amounts of energy at distances of thousands of light years, and if received, it can be easily detected in many ways. And so Tesla's sort of setting the scene for this idea that radio waves might be a good way to communicate if there's other intelligent life out there, and if they've developed the capability to transmit radio waves into space. He did this sort of back-of-the-envelope calculation and figured out that at distances of thousands of light years, a substantial fraction of the distance across the galaxy, that we could hope to pick this up. And I'm going to talk again some more in the second lecture about some of the tools and the technology that we use to do that. But this was, again, in the early 20th century, around the same time that there was an increasing fascination with Mars, with the beginning of the construction of large telescopes. So there was an astronomer, Schiaparelli, an Italian astronomer, who noted through the sort of primitive or sort of relatively low-quality telescopes at the time, what he termed canali, meaning channels on Mars. But the word was sort of mistranslated into English as canals, and Percival Lowell in particular in the 1890s was convinced that these were irrigation canals built by Martians. And so there was sort of this kind of Martian frenzy, really, particularly in the 1920s when Mars was at its closest approach to Earth. And of course, the beginning of ideas in fiction of Martians, and it was considered sort of quite reasonable at the time that Mars might be inhabited by intelligent aliens. So in 1924, Mars was at its closest to Earth that it would be in a century, and there was an astronomer, David Todd, and an engineer, Charles Jenkins, who decided to listen out for potential signals from the Martians. And they actually convinced the US Navy to impose radio silence for 5 minutes at the top of each hour for 4 days so that they could listen for signals coming from Mars. And they used what they termed a radio camera. So it converted the radio signals into optical flashes that left imprints on a 38-foot roll of photographic paper that you see here. And the radio itself was a radio that they had, it was originally designed for use in the trenches in World War I. And they connected this up to a dirigible that was flying at a height of 2 miles with an antenna attached to it. And they picked up some signals, and they got quite excited. You see these signals recorded by Jenkins just about 101 years ago at this closest approach from Mars. We now know that the frequencies that they were observing at, actually those frequencies can't pass through the Earth's ionosphere, and so the things that they were picking up were certainly not signals from Mars. It might have been maybe distant lightning storms, or it might have been sparks from telegraph wires or something. We're not really sure what they were picking up. But it really illustrated that these experiments are really kind of hampered by the fact that not everything that you're picking up is potentially alien. Again, we'll talk about that a little bit later. You shouldn't always go to aliens as your first explanation when you see something weird, would be my suggestion. But we now have the ability to explore through amazing instruments like the Curiosity and Perseverance rovers, which are both driving around on Mars right now. And here you see the Ingenuity helicopter, which was the first aircraft to fly on another planet. And so Perseverance and Ingenuity really, as with Curiosity, tasked with determining whether Mars had the conditions for life at some point in the past. We're pretty sure there aren't little green men running around on Mars right now, but might there have been simple life? Again, sort of taking that example of life in extreme environments here on Earth, might the Martian environment have been more favorable to life in the past? And Curiosity has, on Mars, seen scenes like this, where if you're a geologist looking at this, you see signs of ripples from a shallow lake that was formed here. We really see evidence that liquid water flowed, even for long periods on Mars in the past. And there's indeed signs that small amounts of water have flowed on the Martian surface, even in the recent past. And so maybe, thinking again of those Greenlandic bacteria buried below the ice for 120,000 years, we really want to see, is there extant life on Mars right now, or might there have been life on Mars at some point in the past, or at least the conditions for life. And so again, colleagues at the SETI Institute, I'm not working on the simple life. I kind of take a shortcut to looking for the smart aliens. But colleagues are working on this kind of stuff, again, both from the in situ sampling from experiments like these Mars rovers and by looking at analogs of these conditions on Earth. But our spacecraft have gone even further out into the solar system. The Cassini spacecraft flew out past the orbit of Saturn, took this amazing picture. This is a mosaic of images showing the Saturn system looking back. You see the rings backlit by the sun here. And so, being able to send these space probes out a billion kilometers out into the outer solar system and have them send data back about the conditions has also led to the realization that in some of the moons of the icy of the gas giant planets in the outer solar system, some of these icy moons have evidence of liquid water below the surface of the ice. And so you see here these geysers that are spewing up through the cracks on the moon Enceladus here into space. And there are ideas of sending missions that will fly through these plumes, sample them, look for biological material. Might there be life in these subsurface oceans on these icy moons? So there's even other places in the solar system where we think there's a possibility that life might arise. And this, captivated me at a young age. Growing up in England, I obviously was sort of excited about space, and I guess excited about the United States at the time as well, where I've ended up living in the San Francisco Bay Area. And I had books that laid out, all of the planets, the 9 planets in the solar system. I got to apologize. 19 years ago today, Pluto was demoted from the status of a planet. I know I wasn't actually at that meeting of the International Astronomical Union where it was downgraded, and I apologize again, but in return we've given you thousands of planets beyond the solar system. So since I was a kid growing up in England, we now know that planets are common. These are artists' impressions from a Bay Area artist, Lynette Cook, of some of these planets, a lot of them giant gas planets like Jupiter, other small rocky worlds, and in the middle of this image, Lynette has painted the Kepler spacecraft, which has really been an incredible tool for discovering these planets. And we'll talk a little bit about how that works later in this talk. But I wanted to give you a sense of scale initially. So this is the Voyager 1 spacecraft. So it was launched when I was about 1 in 1977. And for the past 47 years, it's been traveling out into space, and it's now a distance of about 15 billion miles from Earth. And it's traveling at a speed of 38,000 miles per hour. And at that speed of 38,000 miles per hour, to get to the nearest stars, so to get to the Proxima Centauri system at 38,000 miles per hour would take about 75,000 years. Space is big. It's really, really big. And so our chances of actually sending spacecraft to sample the conditions around these nearby stars in the near future certainly are really far-fetched. Oh, we're seeing some pretty cool icebergs out the window there if folks want to just pause for a minute and enjoy the scenery. So, yeah, space is really big. Here's the moon and the Earth to scale. Now, the relative sizes are to scale here, but the distances are not. So I'm going to have a little quiz here. Well, I just told you that was not to scale, but here's another couple of examples. So I gave you at least part of the answer here. So I don't think anybody thinks that A is the correct scale here. Who thinks that B might be the correct scale of the Earth and the Moon? And who thinks that C might be the correct scale? Okay, well, you're all wrong, because actually this is the correct scale of the Earth-Moon system. The Moon is, quite far away on this scale. And then we're going to shrink this down, and we're going to see, okay, how big is the Earth-Moon system compared to the distance to the Sun? And here again, so the Sun is to scale here on the left, and that little bar on the right is now the distance from the Earth to the Moon. And at this scale, again, just to kind of give you an idea of the scale of the galaxy and the distances to the nearest star on this scale would be 2/3 of the way back to Reykjavik. And this kind of gives you an idea of how difficult it is to find planets around other stars just by taking pictures of them. Imagine putting this screen 500 miles away and then trying to observe it and trying to detect the Earth, which is hidden in that little bar to the right there, in the glare of the sun off to the left here. How are we going to do that? How can we even find these planets around other stars? How can we build the technology to do the equivalent of picking this planet out from the glare of the sun at 500 miles distance? Well, I showed you this picture of Saturn. We can send space probes into the outer solar system and take pictures of Saturn. And a cool thing, maybe some of you have spotted this in this picture, but actually you're all in this picture. All your friends and family are in this picture. Your favorite celebrities, your favorite or least favorite politicians are in this picture. Because here's the Earth, this little pale blue dot, spotted by the Cassini mission by this robotic spacecraft of a distance of 1 billion miles, just hanging out there between the rings of Saturn. And so, this is, again, sort of beautiful and humbling, and I think gives us context. But it also, in this specific example, shows us how difficult it is to take pictures of planets, right? This is from 1 billion kilometers away, and now we're trying to do this, taking pictures of planets from distances of at least 10,000 times further than the Cassini spacecraft was able to go. So I'm going to tell you a little bit about how we do that. And it's kind of like looking for a firefly in the glow of a searchlight. You have to block out the searchlight if you want to take a direct picture, and there's an instrument on the Keck telescope in Hawaii that enables us to do that, along with a big laser that they shoot up, sort of Star Wars style, into the sky that corrects for some of the effects of the atmosphere that causes stars to twinkle. Astronomers don't really like the nursery rhyme, twinkle, twinkle, little star. We'd rather our stars be nice, sharp points of light. And so with tools like adaptive optics, we can take images like this one. This is actually 7 years of data from the Keck telescope, and I think the animation should... no, I guess the animation probably happened already, and I'm going to try and go back. Oh, did I not get the animation there? Well, that's a shame. What you would see in this animation is these little dots, so that the star is blocked out by what we call a coronagraph in the middle there, so the location of the star is this yellow dot, but what you should have seen in the animation is the planets moving around in orbits here, and so this is direct imaging of planets around a star, but these are big planets in sort of far out orbits, so they're sort of planets that are more like the mass of Jupiter in our own solar system, and they're on orbits that take between 40 and 400 years in this example. The James Webb Space Telescope has also been able to take pictures of some large planets at large distances around nearby stars. But again, finding Earth-like planets in the glow of their parent stars is really challenging. And so we use indirect methods. And one of them is called the radial velocity method, or you can think of this as the wobble method. And essentially, it's been described as like walking an invisible dog. So if you take your invisible dog out for a walk and it's pulling you around on the end of the leash, you could tell by how much you're being pulled around whether it's a small invisible dog or a large invisible dog, right? And so the planet isn't being seen directly here, but the gravitational leash that attaches the planet to the star causes the star to wobble around. But the planets are smaller than the star, considerably less massive than the star, and so this pull on the star is relatively small, and it pulls it backwards and forwards and causes a red shift and a blue shift in the light. Essentially the same effect, the Doppler shift, as when you hear a siren of a police car going past and the pitch changes. The frequency of the light changes as the star is moving backwards and forwards. And so we can measure those precise changes in the frequency of the light and look at the wobble of the star and thereby determine the mass of the planet and the orbit of the planet. And these are incredibly difficult measurements to make, that we can get precisions of meters per second in the motion of these stars. And essentially this is like saying the change in color of my shirt, whether I'm walking towards you or walking away from you. We can measure that with the instruments that we have on these telescopes, so that precision, it's really kind of incredible. And so about 600 planets have been detected using this wobble method, the radial velocity method, including one of the first planets to be discovered around a sun-like star, this Jupiter-like planet around the star 51 Peg. But there's another method that we can use, and I alluded to this when I showed those pictures of the Kepler spacecraft earlier, which uses this method. that if you happen to be aligned with the orbit of the planet around the star, sometimes you'll see the planet pass between you and the star. Maybe some of you saw the transits of Venus a few years back, where we saw from Earth the planet Venus go between us and the sun. If you're looking at distant stars, then you can also see these little dips in the light, and it's only sort of at a percentage level, basically. Again, if you're lucky with this alignment, where you're in the plane of the orbit of this planet, you see that little dip, and then you can, again, infer the properties of the planet by, I'll try and play this animation again here. Yeah. So here we're looking down on the system, and then we're going to turn, and you'll watch this curve on the left here, this light curve. So the light is at some constant level, and then as the planet passes in front of the star, there's a dip, and as it exits the other side, the light returns to the original level. And by measuring the length of that dip and the depth of that dip, we can tell the properties of the planet, and that's how we know whether it's a Jupiter-like planet, a massive planet, and we can tell if we see two of these transits, we can tell the period of the orbit, and then we can use essentially kind of the physics that goes back to Kepler and Newton to determine the mass, and thereby, if you know the mass, you know the orbit, you know the distance, you can figure out what the temperature might be on the surface of that planet, and whether it's a hot planet that's close in to the star, whether it's a cold planet that's further away, or whether it's in the Goldilocks zone, not too hot, not too cold, just right, the Goldilocks zone, or we also call this the habitable zone around the planet where liquid water could exist on the surface. And again, you know, the Kepler spacecraft has used this method to find thousands of planets around nearby stars. So even though poor Pluto got demoted 19 years ago, in the course of time, we've now discovered thousands of planets, and I've only talked about two of the methods that we use to discover them, but there are a few more that we can get into as well in Q&A. So the habitable zone around our own sun, shown in the middle here, this green zone, Venus is very close to the inner edge of the habitable zone, but Venus has a runaway greenhouse effect, and so certainly the surface is very inhospitable to life, although there are some ideas that there might be life in the clouds of Venus. Actually, the temperatures and pressures up in the clouds are not that dissimilar to temperatures where we see organisms surviving on Earth, and so this is a goal to send missions to Venus. There's actually been some sort of controversial claims that there have been what we call biosignatures, in other words, signs of biology, in particular the detection of phosphine in Venus's atmosphere. I think a lot of scientists think that this is not a bona fide biosignature, but it's nevertheless sort of somewhere that's interesting for future life detection missions. And then we talked about Mars already. Mars is out towards the outer edge of the habitable zone, but Mars lost most of its atmosphere in the past. But again, we're trying to see could there have been life, certainly early in Martian history. And then Earth is, you know, nicely in the middle of this Goldilocks zone here, where liquid water could exist on the surface. But you'll recall, you know, I talked about those moons of the gas giants, that even places that are outside of the habitable zone can have potentially liquid water below an ice crust on a moon, for example, or maybe would have organisms that don't need liquid water to survive at all. But the focus for NASA certainly has been follow the water, basically find out where water could exist in our own solar system and where water might exist on exoplanets, and then design missions that search for these biosignatures in those environments. And so, you know, we now know of examples of systems shown in the top here, the Kepler 22b planet in the Kepler 22 system, so again discovered by the Kepler spacecraft, gets this catalog number. The star is not quite as bright as the sun, so the habitable zone is a little further in, but this planet, which is sort of what we call a super-Earth, so it's more massive than Earth, again, its properties deduced from those transits, is orbiting in the habitable zone. And so, again, systems like this are a good place to do follow-up if you want to try and find signs of life. So here's an artist's impression. Again, you know, we don't have direct pictures of these. We have to rely on the artist's impression, but this is an artist's impression of Kepler 186f. And this is 1.1 Earth radii, so a little bigger than the Earth, in the habitable zone. So a handful of these are known. We only know of a handful of Earth-like planets in the habitable zone of their parent stars, but we then can infer, just by sort of counting the number of stars that we've looked at and counting the number of habitable zone planets, that about 20% of stars have an Earth-like planet in the habitable zone. And so getting back to what I was saying earlier, right, we know that the ingredients for life are everywhere, not just here on Earth, but everywhere in space, this recycling of material from supernovae. And we know that the we now know that the conditions for life are everywhere. And so, if you're disappointed about Pluto, again, I'm sorry, but we have lots of kind of cool places to make up for this. So about 200 billion stars in the Milky Way. Most of them have planets. So there might be something like 40 billion habitable planets in our galaxy. And again, that's not to mention things like the moons of these gas giants. And our galaxy is just one of many. So this is the Hubble Ultra Deep Field. So what you're looking at here is a region of the sky that's about the size of a grain of sand held at arm's length. And the Hubble opened its camera shutter and stared at this position of sky for a total of 11 days. And it saw this incredible vista here. And you look up at the night sky and you see a lot of stars. Here's a star. Here's a star. You can tell these are stars because they have these little diffraction spikes around them. Pretty much everything else in this image is a galaxy. That's a galaxy, that's a galaxy, that's a galaxy, that's a galaxy. About 10,000 galaxies in this image. So you're looking at a grain of sand-sized region of the sky held at arm's length. This star is about 10,000 times too faint to be seen with your unaided eye, and so this would appear like a completely blank region of the sky, and the Hubble sees 10,000 galaxies in this image. I mean, really incredible. And this is not a unique, like weird direction that the Hubble happened to look in. This is repeated all over the sky, wherever you look. Imagine that replicated over the entire celestial sphere. So trillions of galaxies in the universe, just the observable universe. Tens of billions of habitable worlds per galaxy. Where is everybody? Okay, this is Enrico Fermi. You may have heard of Fermi's paradox. He probably wasn't the first person to ask this question, and it's not really a paradox, but it is kind of an interesting question, right? If the conditions for life and the ingredients for life are everywhere, why have we not found life beyond Earth yet? So I want to get back to the transit of Venus here. So this is a picture of Venus transiting the sun taken by the Hinode mission. And you can see here the atmosphere of Venus that's backlit by the light from the sun. And so we can do also these experiments, again, with these very challenging experiments with very high-tech instruments that we can look at exoplanets as they transit their parent stars, and we can try and tease out the effect that the atmospheres of these planets has on the light that's passing through as the planet transits across the star. And so you can see here the backlit atmosphere, and then again, artist's impression here of another planet called K2-18b, and we know that this is a world that has a hydrogen-rich atmosphere. We think it might have a liquid ocean, so we see basically the starlight as it's passing through this atmosphere, and it leaves the imprints. The absorption of light has certain signatures on the light from the star as it's passing through here. And again, sort of controversial claims here. Some of you may have read about this in the media last year, that when you split the light up into its constituent colors, you see these wiggles here, which are signatures of things like methane, carbon dioxide, and then there's weak evidence for this dimethyl sulfide, which on Earth comes entirely from phytoplankton. And so, the authors of this study suggested we're seeing this dimethyl sulfide in the atmosphere of K2-18b. There's been a lot of pushback on this, and I think a lot of astronomers' problems with this study are, well, first of all, you've got to convince me that you detected something. And you see from these wiggles here, okay, they're like, well, I think we detected something here, but it's sort of very sensitive to how you fit the line through this data. Then you've got to convince me that the thing that you've detected is the thing that you say it is. You've got to convince me that it's dimethyl sulfide. And thirdly, you've got to convince me that if it is dimethyl sulfide, then it's coming from biological processes and it's not some sort of natural phenomenon. And so I think this study sort of hasn't convinced a lot of people in the scientific community on all three of those counts, but it's certainly sort of interesting and illustrates that here in this spectrum from the James Webb Space Telescope, that we have the tools and techniques to do this, again, for a handful of planets that are relatively, around stars that are relatively close by to Earth. So this is sort of the cutting edge, really, of these kind of remote sensing biosignature searches. And in the next talk, I'm going to talk about what we call technosignatures. So by analogy with biosignatures, right, science of biology as a proxy for life, here on Earth we have technology, particularly radio transmitters. And you recall that quote from Tesla from 1937 that he calculated that those radio emissions from Earth would be detectable at distances of thousands of light years. So we can only do these biosignature searches for a handful of stars, but if there's other technology out there, then the region of the galaxy that we can sample contains millions of stars. So even if technological life is relatively rare compared to simple life, we can design experiments that hopefully can detect this. And again, I'm going to talk about that a little bit more in the next talk. But I want to go back to Mars. You can actually buy a piece of Mars online. It'll cost you about $200 a gram. How can you buy a piece of Mars? Well, it's because the solar system is kind of like a game of pinball, right? There are things smashing into each other all the time. We sometimes get meteorites that land on Earth, and sometimes meteorites land on Mars and leave impact craters. You see the craters on the moon, of course, when you look up at the moon. Bits of the moon get blasted off, bits of Mars get blasted off. And then some of those, after kind of flying around the inner solar system for a while, can land on Earth and be recovered and be identified as pieces of Mars because they have unique geology. I'm sure Brent could probably enlighten us a little bit more as to what the geological differences might be. But they've also found bits of the Martian atmosphere that are trapped inside some of these rocks and looked at the composition of that and determined these things definitely did not come from Earth. We also, by the way, find other meteorites that contain bits of the asteroid belt or that contain bits of sort of early planetary bodies, if you like, that were forming in the solar system. And some of these are quite mineral rich because they were essentially the cause of some of these protoplanets that then got broken up. And so, then you don't have to dig all the way down to find these. You can recover them, and it's one of the reasons why meteorites are pretty interesting in terms of telling us about the history of the solar system. But also, there are ideas that we might be able to go out and mine the asteroid belt, at some point in the future, maybe, and get access to some of these minerals. The sort of echoes of mining the minerals in Greenland here, maybe, sort of questions of kind of exploitation of resources that come to mind here as well. But again, you can buy a bit of Mars online. You can buy these genuine Martian meteorites online for about $200 a gram. And one of the interesting things is that when scientists have studied these Martian meteorites and looked at the mineralogy, they've realized that some of them were not exposed to sterilizing temperatures at any point during their journey from Mars to Earth. They were blasted off Mars and they traveled around for a bit, but they were never cooked to the extent that if there was life in these rocks, that it might have survived. And again, recall that Greenland bacterium that survived for 120,000 years under the ice, right? And life can survive in much more extreme environments than you might initially imagine. And so there's this idea that life could potentially hop between planets. And if we find life on Mars, maybe it's life that got blasted off a bit of the early Earth and then found some conditions that it liked there on Mars. Or maybe life on Earth started somewhere else and was blasted off from Mars or somewhere else and landed on Earth. So maybe we're all Martians, actually, which would be kind of interesting. But we don't really have answers to these questions yet, but we do still have a lot of questions. And I think something that's quite profound for me is that even if we find nothing, then that's still a pretty profound result. Earth is the only inhabited planet we know, and this also, I think, sort of really gives us additional impetus to protect the planet, right? To protect this one habitable or inhabited world that we're aware of in this island Earth. And really, it's incredibly fragile when you look at an environment like this, and in particular, if you look at a video like this taken from the International Space Station. When astronauts go up into space, they often describe what they term the overview effect, which puts the planet into context. And I think, again, sort of coming to places like Greenland, we see things contextualized. We see life contextualized. We see the fragility. We see really how beautiful these environments are. But you're seeing in this video from the space station this thin band of the atmosphere, and you're actually maybe even kind of catching some of the aurora there. This air glow from something like 50 miles up. And it's kind of cool. There was an astronomer, Fred Hoyle, who noted that space is not very far away at all. It's only an hour's drive if your car could go straight up. So it's about 60 miles from the boundary of space here. So you're actually closer to space now than you are to, I'm going to mangle this, Pilatok. where we made our landing yesterday. You're closer to space than you are to the villages that we met yesterday, and that's kind of mind-blowing to me. And all life on Earth is contained within this little thin layer that's less than 1% of Earth's diameter. And so, you know, if we find out that we really are alone to the best of our knowledge, then I think, again, it gives additional impetus to protect what we have here. It's a quote from Neil Armstrong here, when he was on the moon, he said, "It suddenly struck me that tiny pea, pretty and blue, was the Earth. I put up my thumb, and I shut one eye, and my thumb blotted out the planet Earth. I didn't feel like a giant. I felt very, very small." And there was every 10 years, the astronomy community in the US reviews the state of the field and the state of the facilities. And there's this nice quote that I'll leave you with from the 2020 Astronomy Decadal Review. "It's an exciting time in which to practice the astronomical craft as humanity edges ever closer to being able to answer the age-old question, are we alone? It is humbling and exciting to contemplate that the question of whether life exists elsewhere could be answered with a technology humanity now possesses." And we're going to talk a little bit more about that technology, again, with a focus on my work as a radio astronomer and trying to pick up signals from aliens. And I'll talk about that in the next lecture. But for now, I'm happy to take any questions. Thank you.